Hello everyone. In this video, we shall discuss piecewise defined functions and its properties, as well as on how to sketch the graph of piecewise defined functions. So what are piecewise defined functions? A piecewise defined function f of x is a function composed of k several subfunctions, which we shall denote by f sub 1 of x, f sub 2 of x, up to f sub k of x. And these subfunctions are defined on pairwise disjoint sets or intervals, which are denoted by a sub 1, a sub 2, up to a sub k. So pairwise disjoint sets means that every pair of sets or intervals from the following do not have a common element. So here is the notation for a piecewise defined function. So f of x equals f sub 1 of x, which is defined on the interval a sub 1, f sub 2 of x, which is defined on the interval a sub 2, up to f sub k of x, which is defined on the interval a sub k. So here is an example of a piecewise defined function. So we have f of x equals 4, which is defined on the interval x is less than or equal to negative 2. Um, Second is we have the x squared, which is defined on the interval from negative 2 to positive 2, but exclusive of negative 2 because there's no equal sign here. And then it's inclusive of positive 2 because there's an equal sign here. And then the third subfunction is x plus 1, which is defined on the interval x is greater than 2. Now observe that this function is composed of a constant function, a quadratic function, and a linear function. So if we recall from the previous lecture videos that the graph of a constant function is a horizontal line, the graph of a quadratic function is a parabola that opens either upward or downward. And then for linear functions, the graph is a straight line that is either sloping upward or downward. So the graph of this piecewise defined function will be a combination of the graphs of the constant quadratic and linear functions. So here is the graph. So whenever we consider the interval from the interval x is less than or equal to negative 2, we are referring to the following interval. So this is x is less than or equal to negative 2. And as you can see, above this interval, we see that the graph is a horizontal line. And this is actually extending indefinitely to the left side. And then for the interval negative 2 up to positive 2, we are referring to the following interval on the x-axis. So this is negative 2 less than x less than or equal to positive 2. And above this interval, we see that the graph is a part of the graph of a parabola. And then when x is greater than 2, we are referring to the following interval. And as we can see, the graph above this part of the interval is a straight line that is sloping upward. Okay, so later, we will have examples on how to graph a particular piecewise defined function. So first, before we graph, we need to understand how to evaluate piecewise defined functions. To evaluate a piecewise defined function, we use the subfunctions defined on the intervals that contains the value of x. So which means that if this is the piecewise defined function, we have to ask ourselves, where is x? Can we find it in a sub 1? Can we find it in a sub 2? Or can we find it in a sub k? So once we find the value of x, then we substitute that value on the subfunction given for that particular interval. So for example, let's consider the piecewise defined function f of x equals x plus 1 defined on the interval x is less than or equal to 3. And then f of x equals 5 defined on the interval x is greater than 3. And then let us evaluate f of 1, f of 3, and f of 6. So for f of 1, we need to find the location of x equals 1. Is x equals 1 in this interval, or is x equals 1 in this interval? So since x is equal to 1, 1 is definitely less than 3. So which means that we're going to use the first subfunction for f of 1. So we substitute 1 here, and then we get f of 1 equals 1 plus 1, which is 2. Now for the second item, which is f of 3, x equals 3 belongs to the first subfunction because 3 here is equal to 3. So that's why we have to substitute 3 here. So we have 3 plus 1, which is equal to 4. Now for the last one, we have f of 6. So x is equal to 6. So that means 6 belongs to the second subinterval because 6 is greater than 3. So which means that f of 6 is equal to the constant 5. So that's how you evaluate a piecewise defined function. Let's have another example. Let's consider the piecewise defined function f of x equals negative 3x minus 4 defined on the interval x is less than or equal to negative 2. And then 6 minus x squared defined on the interval negative 2 up to 3, exclusive of negative 2 and exclusive of positive 3. And then f of x equals 7, which is defined on the interval x is greater than or equal to 3. So let's evaluate f of negative 3, f of negative 2, f of 0, and f of 3. So first, we have f of negative 3. And since x is equal to negative 3, that must be in the first sub interval. So f of negative 3 is equal to negative 3 times negative 3 minus 4, which is positive 5. And then for f of negative 2, so here x is equal to negative 2. So negative 2 is also in the first subinterval because negative 2 is equal to negative 2. So substituting negative 2 to negative 3x minus 4, we have negative 3 times negative 2 minus 4 is equal to positive 2. And then for f of 0, since x is equal to 0, that belongs to the second subinterval because 0 is between negative 2 and positive 3. So substituting 0 here to x, we have f of 0 is equal to 6 minus 0 squared equals 6. And then for x is greater than or equal to 3, for the third subinterval, we use that function for f of 3 because 3 is greater than or equal to 3. So that is equal to 7. Okay, now, so how do we graph piecewise defined functions? So to graph a piecewise function, we identify the type and the domain of each subfunction and determine its graph. So we have to determine if the function is constant so that we know that the graph is a horizontal line. We have to determine if the function is linear so that we know that the graph is a straight line that either is sloping upward or downward. Or we should know that the function is quadratic so that we know that the graph is a parabola that opens upward or downward. Now, for each subfunction, we create a table of values using values of x that are inside its domain or inside the interval. Then we will plot those points to create the graph of the piecewise function. However, for each subfunction, we need to include the boundary points in the graph. So for example, if the domain of a subfunction f sub I of x is a strict inequality, say x is less than a, we substitute a to the subfunction and we represent that by a hollow point with coordinates a comma f sub I of a. So this will be shown later in our examples. And then note that a solid point can always replace a hollow point, but a hollow point cannot replace a solid point. So usually these things will happen at the boundary values of the intervals of each sub function. Okay, so for example, let us try to graph f of x is equal to negative x minus 1 defined on the interval x is less than 1. And also we graph f of x equals negative 2 defined on the interval x is greater than or equal to 1. So first, let's consider the first sub function, which is f sub 1 of x equals negative x minus 1. So this one is a linear function. And since its slope is negative 1, it's a line that is sloping downward. Now, in order to graph a line, we only need 2 points. So since this function is defined on the interval x is less than 1, we will be constructing a table of values. So first, since the boundary is 1, even if it is not included in this interval, we have to use it as a boundary point. So x equals 1 will be substituted here, and then the value of y will be negative 1 minus 1, which is negative 2. So from the origin, we move 1 unit to the right and then 2 units downwards. So this point will be represented by a hollow point because 1 is not included in this interval. And then since we're graphing a line, we need a second point or a second ordered pair, but we need to use a value of x that is lesser than 1. So we can safely use x equals 0. So here negative 0 is actually 0. 0 minus 1 is negative 1. So our second point will be the following. Okay, so we connect these 2 points with a line. So this line is actually sloping downwards because its slope is negative. Okay, and then the second sub function is negative 2. So we have f sub 2 of x equals negative 2, and it is defined on the interval x is greater than or equal to 1. So this one is a constant function, so its graph must be a horizontal line. So again, we will create a table of values, and then we shall use 1 because 1 is the boundary value. So x equals 1. If x is equal to 1, the value of this sub-function is negative 2. And then when we plot it here, 1 comma negative 2 occurs at this green hollow point. But since 1 here is included in this interval, this point here must be a solid point. Now we note that solid points can always replace hollow points. So meaning we can overwrite this hollow point by a solid point. And then we use another value of x that is greater than or equal to 1. So safely we can use x equals 2. So if x is equal to 2, the value of y is still negative 2 because we have a constant function. So the graph here for this point is 2 comma negative 2, which occurs at this position. So connecting these 2 points by a horizontal line that extends to the right, then this is the graph of our piecewise defined function. Okay, next, let's try to graph f of x equals 4 x squared and x plus 1 given in the following intervals. So first, f sub 1 of x equals 4. This is the constant function. So its graph is a horizontal line. So using a table of values, we can use the boundary value negative 2. So x equals negative 2, the value of y is 4. So we plot it on the Cartesian plane as a solid point because negative 2 is included in the interval. And then we can use another value of x that is lesser than negative 2, which is negative 3. And since this is a constant function, the value of y is still 4. So plotting that ordered pair, we get this second green point and connecting these two green points by a horizontal line. That's the graph of the first subfunction. Now for the second subfunction, f sub 2 of x equals x squared. Okay, so we shall use the following boundary values. But x squared is quadratic, so it must be a parabola, and since its coefficient is positive 1, it's a parabola that opens upward. So using the boundary values, we can use negative 2 for x, and we substitute it for this function, so we get positive 4. So plotting it on the Cartesian plane, we get the following. This is negative 2 comma 4. But this one here, no, negative 2 comma 4 is a hollow point. This is a hollow point because negative 2 is not included in this particular interval. However, a hollow point cannot replace a solid point. So this one will still remain as a solid point. And then the second ordered pair here, when x is equal to 2, we substitute 2 to this function and we still get positive 4. So when x is equal to 2, we have y equals positive 4. So that's why we get this point here. Okay, and then we use another value of x that will be inside this interval. So x equals 0 would mean that y is equal to 0. So that means the origin is a point on this graph. So since it's a parabola that opens upward, we connect these 3 points by a parabola that opens upward. And then the third subfunction is f sub 3 of x equals x plus 1, which is linear, and it is defined on the interval x is greater than 2. So using the table of values, we use the boundary value x equals 2 and substitute it here in this function. So we have 2 plus 1, which is 3. So this ordered pair must be represented by a hollow point because x equals 2 is not included in this particular interval. So 2 comma 3 must be a hollow point. And then we use another value of x that is greater than 2, which is 3, and substituting it into this function, we have 3 plus 1. So therefore, y is equal to 4. So plotting 3 comma 4, we get that second point, and connecting those blue points by a straight line is the graph of the third subfunction. So this is the graph of the given piecewise defined function in this slide. Okay, now for the domain and range of piecewise defined function, it's best to inspect the graph. But for the domain of a piecewise defined function, it's just the union of the intervals of the subfunction. So we just get the union of A1, A2, A3, and so on. And then the range will be obtained by inspecting the graph. So for example, in this particular piecewise defined function, since the graph extends indefinitely going to the left side and going to the right side, its domain is the set of all real numbers. But for the range, since this is negative 2, so the lowest value, the lowest y value of the graph is negative 2, and it extends upward. So which means that y is greater than or equal to negative 2. And in interval notation, we write it as follows. Bracket, negative 2, comma, positive infinity, and close parentheses. And then for our second graph here, when the graph extends indefinitely to the left and extends indefinitely to the right side, so the domain is the set of all real numbers. So if you check the x-axis, everything on the x-axis is being covered by our graph. So that's why the domain is the set of all real numbers. But for the range, the lowest value, the lowest y value happens here at the origin, wherein y is equal to 0. So which means that y is greater than or equal to 0 because the graph extends indefinitely upward. So the range can be written as bracket 0, comma, positive infinity, close parenthesis. So this ends our discussion of the piecewise defined function and its properties and sketching its graph. And I hope that you learned something from this video. And please do not forget to subscribe to my channel. Thank you for listening.